Okay, let's dive straight in. We're looking at SynthID-Image, image watermarking at internet scale, this really significant paper from Google DeepMind. And this isn't just theory, right? This is about how they're actually doing it.
Exactly. The absolute core insight here is SynthID-Image. It's a deep learning system built for production, massive scale, designed to put an invisible watermark onto AI-generated images, even video frames.
Invisible and robust, that's the key combo.
Right. It's got to survive out there. And the scale, well, it's Google scale.
Yeah, they mentioned, what was it, over 10 billion images and video frames already watermarked across their services. That's staggering.
It really is. It shows a huge commitment to this idea of provenance. And they benchmarked an external version too called SynthID-O.
Right, SynthID-O. How did that stack up?
State of the art. They tested it against things like trust marks, Digistamp, video seal, the usual suspects. And SynthID-O came out on top for both visual quality, meaning it's really, really hard to see the mark, and robustness.
Lowest perceptibility, lowest brittleness. Basically best at hiding and best at surviving.
Precisely. And this all ties back to their main goals. Effectiveness, it has to work. Fidelity, the quality has to stay high. Robustness against all sorts of image mangling. And security against attacks.
But you mentioned provenance. That seems like the big conceptual shift here, moving beyond just, is this AI, to where did this specific thing come from?
Exactly. Let's unpack that because, yeah, that's fundamental. Why this huge push for provenance now in things like Gemini or, other big AI products.
Instead of just better AI detectors.
Because general detection is, well, it's becoming a losing game. As these generative models get better and better, the outputs look so real. Trying to find subtle statistical clues, it just doesn't scale and it breaks down quickly.
So you can't reliably sniff out the AI-ness anymore if the model is good enough.
Pretty much, yeah. Provenance flips the script. It's not about generic detection. It's about specific origin, establishing the identity, the source of that particular image or video frame.
Okay, but don't we have things like C2PA already? The Coalition for Content Provenance and Authenticity, they're all about metadata tags for origin.
We do, and C2PA is super important for setting standards. But the Achilles heel is the metadata itself.
It's fragile.
Very.
Yep.
Think about it, a simple screenshot, uploading it somewhere that strips metadata, or someone just, maliciously removing it. It's trivial because the tag is attached to the file, not inside the content.
Okay. And that's where the invisible watermark comes in. It embeds that provenance info directly into the pixels or, the data itself.
Exactly, which makes it way more robust. And using deep learning for this, well, that promises you can store more information, a bigger payload, and potentially get better robustness than, say, older methods using wavelets or Fourier transforms.
Although deep learning also means it's potentially vulnerable to adversarial attacks, right? Like fooling the detection network.
That's the flip side, yeah. Security is a constant battle. Now, getting into the tech foundation a bit, SynthID-Image uses a specific approach. It's post-hoc and model independent.
Post-hoc meaning after the image is generated.
Correct. Think of it like this. The AI model, say Gemini, creates the image first. Then, after it's fully generated, a separate SynthID encoder step adds the invisible watermark. It's like stamping a finished painting.
Okay, as opposed to an ad hoc method where the watermarking is somehow built into the image generation process itself.
Exactly. Ad hoc would be like mixing the watermark into the paint as you're painting.
So why choose post-hoc? Doesn't integrating it give you more control, maybe?
It might seem like it, but post-hoc gives them maximum flexibility and deployability. They can use the same SynthID system across loads of different models, current ones, future ones, image models, video models, without having to re-engineer the core generative AI each time. It reduces dependencies.
Okay, that makes sense from an engineering perspective. But wait, if you're stamping it after the fact, aren't you inherently changing the image? Isn't there a quality hit?
Yes. That's the crucial trade-off. Post-hoc methods are inherently lossy. The watermarked image is technically different from the original.
Some ad hoc methods claim they can be lossless, right?
Some do, yeah. But the DeepMind team argues pretty convincingly, I think, that even with a post-hoc method, you can achieve such a high level of invisibility, practically speaking, that humans just can't tell the difference. They frame it as an optimization problem.
Right. So they're minimizing the chance the detector gets it wrong, but with a very strict limit, an epsilon, on how much perceptual difference they can introduce.
Exactly that. Keep the visual change below a human detectable threshold. And then for robustness, the training aims to make sure the mark survives across a whole distribution of common image transformations, things like compression, resizing, cropping, basically, anything that doesn't destroy the image's usefulness.
Which brings us to what you called the conflicting desiderata. This sounds like where the real engineering challenge lies. They're juggling competing demands.
Absolutely. It's the classic quality robustness payload trade-off, or QRP as they sometimes call it. You want perfect quality or invisibility. The mark can't degrade the amazing output of these AI models.
Otherwise, what's the point?
Right. Then you need robustness. The mark has to survive the internet jungle compression, filters, resizing, you name it.
And finally, payload. It can't just be a yes-no, is this AI signal?
Exactly. For real provenance, you need to store meaningful information. SynthID-O, for example, handles a 136-bit payload that's quite large for a watermark.
136 bits. Okay, that sounds like a lot. If they're fighting so hard for invisibility and robustness, doesn't making the payload that big make it, I don't know, easier to find or break?
It's definitely a tension. A bigger payload inherently makes the mark potentially more fragile or perceptible if you're not careful. But it's game necessary for the provenance goal. With 136 bits, you can encode, say, which specific model version was used, maybe which partner organization generated it, if it's through an API, maybe a timestamp range.
So that level of detail is what turns it from detection into actual tracking and origin tracing.
Precisely. It allows for that fine-grained understanding. Now, beyond QRP, they also hammer home the practical stuff, efficiency and security.
Efficiency must be huge at Google scale. Where's the main time crunch? Encoding or decoding?
It's almost always decoding, the detection part.
Yeah.
Encoding, adding the mark, needs to be super fast, like a tiny fraction of the image generation time itself, maybe a few percent overhead.
Okay.
But decoding, think about how often you might need to check an image. Google search, scanning images, internal systems, vetting potential training data scraped from the web. Detection might happen orders of magnitude more often than generation.
So if decoding is slow, the whole system grinds to a halt, practically speaking.
Totally. It becomes unusable at scale. And then there's security. They're not aiming for unbreakable encryption here, are they?
Doesn't sound like it. More pragmatic.
Exactly. They need to defend against basic watermark removal attempts, causing false negatives, and forgery attempts, trying to add a fake watermark to cause false positives.
Makes sense.
But the main focus seems to be on making black box attacks computationally infeasible. They assume most attackers won't have the source code or the model weights, just the watermarked image and standard tools. Stopping a dedicated insider or someone with full white box access is probably impossible, but stopping millions of casual attackers is the goal. Robust training is key there.
The paper goes into incredible detail on testing. Given that standard image metrics like PSNR or SSIM don't always capture how humans see things, how do they really nail down the quality and invisibility testing?
Yeah, it's kind of funny. After all the complex deep learning, the gold standard for invisibility is basically just asking people, hey, does this look weird? They relied heavily on human evaluations.
So like A/B testing for watermark.
Pretty much. They ran internal studies, show raters two images, one watermarked, one not, side by side. Ask them to pick the watermarked one. The goal is for the raters to perform at chance level, around 50%. If they can't tell, the mark is truly invisible.
Okay, that makes sense.
And critically, they also did external studies that felt more realistic. Raters saw only one image, either original or watermarked, and were just asked, do you see any artifacts or problems? Simulates just looking at an image online.
And they didn't just use standard pretty pictures, did they?
No, that's important. They specifically included tough cases, black and white images, simple logos, images with smooth gradients, stuff that watermarking often struggles with, but which gets generated all the time.
Okay, so thorough on the quality side. What about robustness? They built their own benchmark suite.
Yeah, a set of 30 basic transformations, things everyone does to images online.
Like what specifically?
Oh, various types of compression, like different JPEG quality levels, resizing, cropping, adding noise, changing brightness or contrast, applying common filters, think Instagram filters, even small rotations or flipping the image left-right. They group them into categories like color, spatial, noise, etc.
Things that shouldn't break the image's meaning, but might break a fragile watermark.
Exactly, and the results, SynthID-O really shown here. They calibrated the detector to be very cautious, a 0.1% false positive rate, meaning almost never wrongly accusing an unwatermarked image.
Very low tolerance for false alarms.
Right. And even with that strict threshold, SynthID-O's detection rate, the true positive rate, was significantly better than the baselines, especially under combinations of attacks.
How much better?
Well, in aggregate random transformations hitting the image with multiple random changes, SynthID-O was the only one getting over 99% TPR. And in their worst-case aggregated test, it beat the next best competitor by over 16 percentage points. That's a huge margin in practice.
Wow. Okay, so that's a decisive win on robustness, even with that big 136-bit payload.
Exactly. It shows they managed that QRP trade-off incredibly well, getting high accuracy for both the overall code and the individual bits across all those tough transformations. That's the technical muscle that makes real-world provenance feasible for different models and partners.
So moving beyond the model itself, what about actually deploying this monster system? They talked about different scenarios, right?
Yeah, the realities of running this at internet scale, as the title says. That forced some very pragmatic engineering choices. They identified 3 main contexts: running it purely internally within Google, offering it as a service to third parties, and potentially dealing with open source models where attackers have more info.
And the amount of information an attacker has changes drastically between those.
Totally. This also influenced how they make the final detection decision. They moved away from making assumptions about, say, how the bits in the watermark might be statistically distributed.
Because those assumptions might not hold up in the wild.
Precisely. Real-world noise and transformations can mess up neat statistical assumptions. So instead, they use something called non-parametric conformal p-values.
Okay, that sounds technical. What's the upshot?
The upshot is it gives them a more reliable way to measure confidence in a detection without making strong assumptions about the underlying data distribution. It helps calibrate the system against real-world messiness and, crucially, helps control that false positive rate reliably.
Got it. More robust decision-making. They also mentioned versioning. That sounds like a long-term headache.
Oh, absolutely. Think about it. The encoder, the thing that writes the mark, has to be stable. An image watermark today needs to be detectable years from now. So that defines a version.
But the decoder needs to keep evolving.
Right. The decoder, the detector, needs to be updated constantly to handle new image formats, new attacks, maybe improve efficiency. So in production, Google systems need to be able to detect multiple versions of the SynthID watermark simultaneously. Version 1, version 2, version 3, potentially forever.
Adds complexity. And they were clear this isn't a magic bullet, right? Watermarking is part of a bigger picture.
Yeah, very much so. It's a crucial piece, but not the whole puzzle. They talked about combining it with C2PA metadata. SynthID provides the robust internal mark. C2PA provides a standard way to potentially expose that provenance publicly.
Complementary tools.
Exactly. And also combining it with robust fingerprinting or perceptual hashing.
How does fingerprinting help?
Fingerprinting creates a compact representation, like a hash, of the image's visual content. It helps mainly with detecting forgery. If an attacker tries to slap a valid SynthID watermark onto a different image, the watermark might say, "I came from Google," but the fingerprint wouldn't match the fingerprint of the original image Google actually generated and watermarked. It adds another layer of verification.
Okay, so pulling it all together. What's the big takeaway here? This paper feels less like just announcing a new model and more like a blueprint.
I think that's exactly right. It's a roadmap, battle-tested at incredible scale, for how you actually build and deploy an invisible watermarking system for media provenance in the real world. They demonstrated that you can balance quality, robustness, and payload even when the demands of the internet are trying to pull them apart.
It really shows the difficulty of taking these ideas from theory into a massive, messy adversarial environment. The operational success at billions of images is pretty remarkable.
Definitely. It marks that necessary transition from just theoretical models of robustness to these highly pragmatic, engineered, scalable systems. SynthID is like an internal ID card for AI-generated content.
But as they noted, it's mainly internal for now, or requires their specific decoder. The wider challenge remains, doesn't it? For this to really tackle misinformation broadly, the verification needs to be more open.
Absolutely. SynthID alone, being proprietary, doesn't solve public trust. It needs integration with open standards like C2PA, maybe involving cryptographic signatures, so anyone can potentially verify the provenance claim. Widespread adoption across the industry is key.
Which leads to a final thought. Given how complex it is to maintain detection for all these internal watermark versions over time, could the long-term future of provenance rely less on individual companies maintaining proprietary detectors and maybe more on something like a decentralized, transparent ledger? a shared record of origins. Just something to think about as you navigate the web today.